Hello, everyone, and welcome to today's webinar on Atom Probe Tomography, APT. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Dr. Shangyu Shah, one of our project managers at Nanolab Technologies, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Dr. Pritesh Parikh, scientist at Nanolab Technologies, a Eurofins company.
Thanks, Rena. Today's topic will cover the technique atom probe tomography and its use to understand and solve material challenges at the nanoscale. I would like to thank all our attendees for taking the time to join this webinar. Before I get started, I'd like to introduce myself. I'm Pritesh Parikh, a scientist here at Nanolab Technologies, and I have a PhD in nanoengineering from UC San Diego. I currently have over 4 years of experience in materials diagnostic, primarily using focused ion beam and atom probe tomography, and my expertise lies in semiconductor devices, specifically FinFET structures and energy materials, both solar panels and lithium-ion batteries. The outline of today's webinar will start with an introduction to Nanolab Technologies and the Material Science Division at Eurofins, followed by the Smart Chart, an overview of APT or Atom Probe Tomography, specimen preparation, specific expertise for APT at Nanolab Technologies, application cases which were investigated in-house over here to demonstrate APT use, followed by the challenges and the concluding remarks. So Nanolab was founded in 2007 and it joined the Eurofins Material Science Division and the EAG family in 2018. Nanolab has more than 44 technical employees with an advanced degree, and together we have over 350 years of collective experience in the industry. Our client portfolio includes both industry partners and academic institutions. We are ISO certified, and we provide a fast turnaround with a broad range of techniques and services that can provide complementary information, such as advanced microscopy, atom probe tomography, failure analysis, and surface analysis. Now, to run the lab with such a large volume, logistics become really important, and we have a very strong support team, the production control team, who ensures that our customers are always taken care of and our lab operations run very smoothly. Nanolab offers many advanced characterization tools, some of which are highlighted here, such as your FIB-SEM, XSEM, X-ray photoelectron spectroscopy, 3D X-ray tomography, as well as atom probe tomography, and aberration-corrected TEM, and STEM EDX and STEM EELS. Nanolab is part of the global family of EAG Laboratories and the Eurofins Material Science Division. EAG was established in 1978. We have labs at over 20 locations in 7 countries, and we offer more than 40 analytical techniques with over 300 instruments. We have 600 scientists, engineers, and support career scientists. Our expertise combined with leading state-of-the-art technology and equipment enables us to leverage the power of science and engineering to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. APT is unique since it's offered only at our Milpitas location in California in the Bay Area. So now let's take a look at the SMART chart. SMART stands for Spectroscopy, Microscopy, Analytical Resolution Tool, and it shows the techniques we have available at EAG plotted to show the attributes related to the spot size or the spatial resolution on the x-axis and the detection limits or the detection range on the y-axis. The techniques shown in the plot are color-coded according to the description here, shown here on the lower left. For example, techniques shown in dark blue correspond to elemental information, and the ones shown in green correspond to imaging information. The x-axis shows the range of the spot sizes, all the way from 1 centimeter on the right down to 1 angstrom on the left, and the y-axis shows the concentrations in atoms per centimeter cube, or in atomic concentrations, all the way from 100% on the top to 10 parts per trillion at the bottom. So within the box, you can select which technique you need based on the detection limit and the size of your analysis area. So for example, if your analysis area corresponds to about 10 micrometers and the detection range that you're looking for is between 10 raised to 16 to 10 raised to 17 atoms per centimeter cube, then TOF SIMS or time of flight SIMS is the technique of choice for you. Apart from the technique shown inside the chart, there are also some techniques outside which don't quite belong within the chart because they don't have both a spot size and a detection range associated with them. So the techniques shown here on the left only have a detection range such as NMR, ICP, as well as GCMS as they consume the entire sample. And the techniques shown on the bottom here, such as SEM, AFM, don't have any kind of detection range. Now, as you can see over here, atom probe tomography actually is a part of this EAG chart here since we provide the service, and it has a high spatial resolution until nanometer scale, as well as very high chemical chemical sensitivity all the way until 10 parts per million. Now, knowing that atom probe tomography can provide this high spatial and chemical resolution, the next question which arises is how does it actually do that? So let's discuss a little bit more about this. So what you have is individual specimens that have an apex radius of less than 100 nanometers at the tip, and these are shown here as green rods. And they are attached onto silicon micropost and placed under the effect of a high voltage bias with respect to a local electrode. Now, the atoms which are present in this tip on the surface are actually in the minima of this potential energy landscape. But in the presence of this field, the potential energy landscape actually changes, and you need just a little bit more energy, which is provided either with a pulsed laser, specifically for ceramic and semiconducting samples, or a pulsed voltage specifically for metallic samples, in order to cause these atoms or ions to field evaporate from the surface. Now, the field at the tip apex is proportional to the voltage, directly proportional, and inversely proportional to the radius. So high voltages of a few kilovolts and a low tip apex radius of less than 100 nanometers allows ions to very easily emit from the surface. The sample is also cryogenically cooled down until a temperature range of 25 to 80 Kelvin. And this ensures that any kind of atomic position changes because of thermal vibrations are suppressed, and you get a true idea of what the atomic position is. And how does it do that is, so let's talk about that a little bit more, is these field evaporated ions first hit a position sensitive detector. And on the position sensitive detector, based on the X and Y position, we can back calculate an X and Y position of that atom back onto the specimen. Apart from that, the time of flight is also measured for each ion being emitted, and that time of flight is converted into a mass to charge ratio, which is used to identify chemical composition. The atomic evaporation happens one after another, and the sequence of the ion evaporation is actually able to give the Z resolution. So together, after the reconstruction process, what we obtain is a true 3D map, a detailed map of the type of ion and its location within the specimen. And you can obtain this both with atomic scale resolution, specifically in the Z direction, as well as a very high chemical sensitivity until parts per million, truly at nanoscale volumes. So this is what atom probe tomography really does. But the question now is that where is it that you really need this kind of a nanoscale analysis? And the answer actually lies in the current and the next generation of technology and the devices which already have problems at the nanoscale. So let's take a look at certain examples here and the challenges associated. The first example is with semiconductor devices, specifically FinFETs. So over here, the technology node is already at 10 nanometers and 7 nanometers and going continuously lower than this. These devices are complex in their 3D shape, and they contain dopants which affect the specific electronic properties, such as the saturation threshold voltage. They also contain germanium in the PMOS-related devices, which affect the electronic transport. So the challenge here is to actually look both qualitatively and quantitatively what is the dopant distribution in this complex structure, specifically boron-based dopants, which because of its light atomic number are very difficult to analyze with other techniques, as well as looking at the silicon and germanium cap layer in the PMOS devices. On the other end, when you look at lighting-based devices such as LEDs, they have a nanometer scale heterojunction, and they use very specific dopant elements here, both of which actually affect the light emission characteristics. So the challenge is to actually, with very high chemical sensitivity, look at what is the distribution of elements and the dopants within these nanometer junctions. When you look at energy-based devices such as photovoltaics, such as silicon and SIG's thin film solar cells, here the challenge and the issue is looking at charge carrier transport. And charge carrier transport is actually affected by the grain boundary composition for both these types of photovoltaic devices. And if there is any possible segregation of chemical species in the grain boundary, that's important to know for the electronic transport. But over here, the issue is that these grain boundaries can be in any orientation and they don't necessarily have to be flat. For batteries and catalysis, they have nanoscale coatings, dopants, as well as compositional gradients within micron-sized particles, which are actually used to enhance the electrochemical performance. So identification of what the chemical and spatial distribution is of these elements is actually important to establish a structure property relation, and it helps to guide, make the next generation of batteries and devices. So for all of these cases, actually, the requirements are so specific that SIMS as well as STEM EDX and EELS, 1D and 2D techniques fail to provide the required resolution, either the chemical resolution or the spatial resolution or a combination. And this is a space which can actually be uniquely filled by atom probe tomography or APT. And that is what we're going to discuss for today. So based on the operating principles and the current and future material needs, APT has certain very unique capabilities. It has high spatial sensitivity in 3 dimensions until Armstrong levels for metallic systems in the Z direction and until nanometers for oxide-based systems. There is also high chemical sensitivity all the way until 10 parts per million. And more importantly, there's actually equal probability of detection of all of the elements ranging all the way from hydrogen to uranium. So even light elements such as boron and lithium can easily be picked up by atom probe tomography analysis. There is also enough resolving power to differentiate between the isotopes of the elements, which can be used for very specific applications. And the pulse laser allows analysis of ceramics, oxide, semiconductor, as well as heterojunction-based devices. So the chart here now shows a comparison of APT with 2 other conventional techniques which are used at the nanoscale, SIMS and TEM EELS. So when you look at the chemical sensitivity, SIMS does provide a better chemical sensitivity than atom probe. But in terms of the resolution and the analysis area, atom probe is actually truly a nanoscale technique. As well as when you compare with TEM EELS, it does provide 3D information compared to the 2D information of TEM EELS. So just to bring that point home, if you look at a complex structure such as a FinFET, which contains these kind of 3D shapes, the SIMS can provide just a 1D information about the concentration as a function of depth. TEM provides a 2D information, specifically spatial information about the different layers. But atom probe tomography can actually provide a true 3-dimensional information about the entire structure as well as the chemical information. So circling back to all of the challenges which we saw earlier, whether it was elements which have a low atomic number such as boron, whether it was high chemical sensitivity in LED devices or grain boundary orientations or specific elements in battery materials, APT actually satisfies the requirements for all of these material challenges, and it continues to do so even for the future technologies. So at Nanolab, we work with the latest version of the instrument, the LEAP 5000 XR, which has both the laser and the voltage mode capability, which is used to cover a wide range of applications. It also has a reflectron system for enhanced mass resolution, for elemental analysis, and for chemical composition analysis. So now let's talk a little bit about the system itself. It contains multiple chambers. The first one is the load lock, which is the only chamber which is ever exposed to the ambient, and it's used to load the samples or the specimens in and out of the system. Below the load lock is the buffer chamber, which is used for specimen storage, and there is a horizontal transfer rod and a vertical transfer rod which is used to transfer samples between the load lock, the buffer chamber, and the main analysis chamber where the actual data acquisition happens. Above the analysis chamber is the cryogenic head, which is used to cool the specimens down all the way to a low temperature between 25 and 80 Kelvin. And this is to ensure that any kind of thermal vibrations are really suppressed. Apart from this, specimen preparation is also a very involved process for atom probe tomography, and it requires a careful platinum weld to hold the specimen down during the field evaporation because the field evaporation process can create large stress in the material. Apart from that, even the lift out shape is actually as a wedge shape, which is different from what is used for a TEM. And all of this is to ensure that the tip survives better. And finally, an annular milling step is used in order to make sure that the radius right at the tip apex is less than 100 nanometers and the field evaporation happens efficiently. So certain applications also require more complex specimen preparation. Certain examples are shown here. The first one being site-specific preparation. In site-specific preparation, you have certain regions of interest that you are specifically looking at, and you want to make sure that those regions of interest are actually captured in the atom probe tip. On the other end, there are also agglomerated submicron particles where the interest could be looking at the chemical composition, as well as submicron diameter rods. And at Nanolab, we have the capability actually to work with all of these different types of morphologies and complex sample preparation. Overall, specifically for Atom Probe, we provide a very comprehensive solution here at Nanolab, right from the specimen preparation to data acquisition, the reconstruction, as well as the analysis. For us, the customer always comes first, so we follow a cycle where first we discuss the project requirements with the customer and identify specific challenges that the customer is looking for. Once the samples and specimens are handed off, we follow all of the protocols and procedures to do the sample preparation, all the acquisition, as well as analysis and data presentation for the customer, as well as any correlation with other techniques as needed. And all this while we make sure that there is reliability and reproducibility with internal validation checks. There is always confidentiality of the customer data, which is protected, and the customer satisfaction. And we make sure that once we discuss the results with the customer on the final end, it's always a conversation back and forth to make sure that we can really build long-term relations with the customer. So based on these instrument capabilities and our expertise here at Nanolab, let's now take some time to discuss applications of atom probe tomography. And as you can see here from the chart on the right, there has been a greater and greater interest in the community for continued atom probe analysis, both in the research community as well as towards industrial applications for different types of material systems. So while this atom probe tomography was primarily investigated and developed for metallic-based systems, there was very easily and a quick adoption of bulk and thin film dielectric as well as semiconductor-based samples for this technique. But over time, there has been novel applications such as batteries, geological materials, biomineralized based materials, as well as fully organic materials such as ferritin molecules. So discussing some examples of atom probe tomography. First, towards the electronic and the optoelectronic industry, which has seen the largest adoption of this technique. So the first example I want to discuss here is actually of a FinFET structure, which was stopped during the fabrication process in order to look at the dopant distribution. So over here, you can see the source, the drain, and the gate, and the fin, which is shown here in the area of interest. And actually, using atom probe tomography, you can see arsenic, which is a dopant, both in the source drain structure, which is shown here in blue, as well as under the gate. And actually, this can help to design the next generation of devices. Apart from semiconductors, there is also applications of APT towards geoscience, where you can specifically look at boron compositions in borosilicate glass, and boron, which is used over here for these glass materials, actually helps with the thermal shock resistance. So looking at the distributions and the compositions of boron can actually help to make better glass materials. On the other end, we can also look at metallic alloys. The example shown here is specifically for a nickel titanium hafnium shape memory alloy. And over here in this alloy, there are these precipitate phases which are formed, specifically an H phase precipitate, where you can clearly see with the composition in that H phase precipitate is there is a lower amount of titanium in that precipitate, which increases in the matrix outside, and the precipitate is actually rich in hafnium. So knowing the composition of this precipitate specifically for alloy materials can help to understand what the strength and the longevity of these materials is. Now at Nanolab, we wanted to specifically demonstrate representative examples which we have investigated in-house here to really show you specific cases where atom probe tomography is really, really useful. So the first example I'm going to discuss today is optoelectronic devices such as LED, which are widely used for TV, lighting, and signaling purposes. These devices have a very complex heterojunction stack. The example shown here is for a blue LED, which contains your gallium nitride and aluminum gallium nitride layers, the P-type and the N-type layers, and sandwiched between them is a multiple quantum well structure which contains indium, which is used to modulate the band gap and provide a true blue LED. The performance of these LEDs are affected both by the polarization efficiency as well as the indium concentration profile. And what we can do using APT is first look at magnesium distribution, which is a common dopant element used for the P-type layer. We can also look at the aluminum concentration profile in these aluminum gallium nitride blocking layers, the indium dispersion laterally in the quantum well, as well as the indium concentration profile, all of which ultimately affect the performance of the device. So let's take a closer look at this now. So this is a representative example of an LED, which first we deprocess down. And then the initial thing is when you look at the mass spectrum that you observe from APT, you see that all the expected signatures for gallium, nitrogen, aluminum, indium, and magnesium have been picked up. Magnesium here is a dopant element, so you can see that we really need to zoom into that region to actually make sure that the magnesium has been picked up. There are also complex ions which have been investigated here, such as gallium nitride, other species, and they are actually part of the field evaporation process of atom probe tomography. So the first thing we want to look at is using a STEM image, what do the different layers look like, the spatial distribution. But when we overlay this with the atom probe tomography tip image, we see that it provides one-step information further, not only looking at the spatial information, but also what is the chemical information for these different layers. So we can clearly see the aluminum gallium nitride layers, the quantum well structure, as well as the superlattice structure. Now, taking a little bit more detailed look at the quantum well, both through the STEM and then through the atom probe for the chemical analysis, we see that the quantum well structure is actually rich in indium, and we can also understand and analyze the composition of the indium in each of the quantum well structures. On the other hand, we can also look at what the dispersion of the indium is, and this can be done by looking at the roughness of an isoconcentration surface. And what an isoconcentration surface is basically a surface which contains the same level or the same amount of indium throughout. So looking at how rough that isoconcentration surface is, which has the same amount of indium throughout, we can actually see how well the dispersion is of the indium element, and it can help us to design the next generation of LED devices. Also, we can look at the superlattice structure over here shown on the bottom and see that the superlattice structure also has indium-rich regions, as well as a magnesium dopant in the p-type aluminum gallium nitride layer. Over here, clearly as a 2D map, we can see where these individual magnesium atoms are distributed. Now we wanted to take this a step further to actually do more analysis on the magnesium itself, because that is something which is elusive using other techniques, specifically because the magnesium exists as a dopant, so it's in very low concentrations, and any kind of clusters of magnesium which are formed are in a nanoscale volume. So they're not possible to analyze using 1D or 2D techniques like EELS, EDX, or even SIMS. So in this example here, we can clearly see how the magnesium is distributed both in a top aluminum gallium nitride and a bottom aluminum gallium nitride layer. And we can see this not only in the front projection, but also when you look at it top down. In both the cases, we can really see how this magnesium is different in both of these cases. And we will show this not only in 2D, but also in 3D also. We can go one step further over here, which is what atom probe tomography is also very useful for, is not only to observe these small clusters of magnesium, but also to understand what is the composition of nanoscale clusters. So when you specifically look at these isoconcentration surfaces of magnesium over here, which is 1 atomic percent right on the surface, we can see that as you're going from outside the cluster to inside, the magnesium amount is actually gradually increasing until it reaches about 8 atomic percent, which is a very high amount inside these clusters. And we can see that these clusters are present not only in 1D, but also in 2D and in 3 dimensions we can see over here. So now let's look at another example. In a separate case, we will now look at 22 nanometer FinFET devices. And FinFETs are basically the building blocks that go into the processors that run our phones, laptops, and all of our electronic devices. And these FinFETs are actually complex three-dimensional structures, as can be seen here with multiple layers and multiple interfaces. And you can see that both in the top view as well as in a cross-section view using the STEM image. Now, these structures also have dopants like boron incorporated into them, which affect very specific electronic properties. And identification of these dopants within the structure is actually really important. Now, boron being a light element, as well as at the concentrations it is used as a dopant for FinFETs, it's actually almost impossible to use even TEM to observe these. So Atom Probe is really uniquely suited here to observe 3D boron distributions. For these specific examples for FinFET devices, we do need to actually process the chipset a little bit further. So we go through a deprocessing step. The first is to actually polish and remove all of the top metallic layers so we can get all the way down until the region of interest. And the second is to etch away the tungsten layer because the tungsten evaporation field for the atom probe and compare that to all the evaporation fields of the other heterojunction layers in here is actually so different that it affects the tip survival. We also make sure that the sample preparation happens uniquely here, and the sample is actually rotated 90 degrees, again to ensure that there's better sample survival under the high evaporation field. So doing all of these processings, what we can see now is actually get a true 3D picture of a tip shape as well as the dopant distribution. And for these specific cases, what we've done here is actually taking cues both from the STEM image and done more analysis on the atom probe to see over here 3 different tips which we have actually combined together in order to form the analysis for an entire single PMOS device, which you can see shown in the red box on the STEM image here. Now, in this image, we can see how the boron is distributed. We can pick up a very small amount of boron, about 0.05 to 0.06 atomic percent. Specifically, though, what I do want to mention, apart from picking up the boron distributions in specific regions, is that the region of interest, which is shown here in red, can actually be sometimes too big to be caught by a single tip for the atom probe analysis, specifically for these complex structures. That is why we did make sure that we're able to run multiple tips and put together the data of successful runs in order to cover that entire single PMOS device. Now let's take a deeper look at this at one of the maps, just to show you an idea of where the boron is. And over here we can see that there is a 6 atomic percent iso concentration surface of germanium. And this surface shows kind of the boundary of the germanium. And you can see that a little bit more clearly here when we take a thinner slice without losing any of the information. And it shows that inside this region, there is actually a higher amount of germanium as compared to outside of it. Again, the way this shape is oriented actually shows that what region we have analyzed here is right at the top of the fin, and the individual boron atoms can be seen very clearly using atom probe tomography. And this is one thing which I really want to stress on, is that observing boron in 3D as specifically at such low concentration is actually not possible using SIM, STEM, EELS, STEM, EDX, any kind of 1D or 2D techniques for these FinFET structures. Finally, I'd like to actually talk about another specific example, which is commercial aluminum alloys, which are widely used for the automobile and the aerospace industry. And they have magnesium, copper, and zinc impurities, which actually affect the structure and the lifetime of these materials. So over here from the mass spectrum analysis, we can very clearly see that apart from the aluminum matrix or the aluminum alloy, we can also observe the presence of magnesium, zinc, as well as the copper impurities. And not only observe them, but also see where they are distributed in 3 dimensions. So the magnesium and the zinc is actually distributed as nanoprecipitates within the structure in the aluminum matrix. And we can do a compositional analysis as shown here in the right, where outside in the matrix, it's primarily aluminum. But as you get into that precipitate, it's actually a large amount of magnesium and zinc and a small amount of copper. And we can actually identify the concentration of each of these elements, which can then help to identify what kind of precipitates are actually present in these alloy materials. Now, such an analysis is actually very easy to do with atom probe tomography, even when these nanoprecipitates are about a few nanometers in all 3 dimensions. So the last thing is to actually observe whether these precipitates are uniformly distributed through the matrix or not. And we can really look at a 3-dimensional movie to see that these precipitates are actually uniformly distributed through the matrix. So whether it's a uniform or non-uniform distribution of a precipitates in the matrix is also possible using atom probe tomography. So like all techniques, even APT has its own limitations, a couple of which is what I want to discuss here now. The first one is the Z-depth correlation or the Z calibration. And over here, the important thing is that this calibration requires an external input. And even with the same amount of atoms which we collect, if the calibration is not done, how the tip shape looks like would be very different. So there are a couple of ways to actually achieve this calibration. The first is to use the known distance of a certain feature, such as a particular layer thickness within the atom probe needle, and use that to calibrate the Z distance. The second is to actually use images captured before and after atom probe analysis. So looking at the tip radius before and after and actually superimposing those images can give an estimate of the total height, which can be used for the Z calibration. The third for specific cases is you can use crystal lattice distance. And the fourth way, which is more commonly used and which I've shown specifically for the LED example, is to actually do a correlation with TEM and stems to ensure that the Z calibration is correct. Another important limitation is the overlap in the mass to charge ratio, which can sometimes make exact quantification difficult. And over here, the specific example which I've taken is titanium 3 plus. So titanium has an atomic mass of 48, and the 3 plus charge state will have a mass to charge ratio of 16, which overlaps with the mass to charge ratio of oxygen plus. Also, for phosphorus, where specifically it tends to form clustered ions, both with multiple charge states, identifying an individual mass to charge peak with which species is present is actually very difficult, and it can lead to an underestimation of the composition. So there are even here two ways to actually overcome this issue. The first is to look at the isotopic presence and the abundance. So atom probe tomography can actually identify individual isotopes. So you can look whether it's a single peak has the isotopes present around it, not only the presence, but also whether they are abundant in the correct ratios, because for naturally occurring element, you should see signatures of all of the isotopes. And you can use that to identify whether it's one element versus the other. The other way is to use peak decomposition analysis, which can help to identify the percentage of each element present within that peak. And both of these can be used to overcome the overlap issues. So having discussed the limitations, I'd finally like to conclude with some remarks for today. So atom probe tomography provides 3D spatial and chemical information of each element simultaneously. As I've shown through the examples here and specific cases where APT is really useful, it can provide cluster analysis, nanoprecipitate analysis, specifically light element analysis such as boron with very high chemical sensitivity, as well as interface and grain boundary compositional analysis. And specifically for APT, this analysis is not limited to interfaces or boundaries which need to be flat or dopants which have to be in 1D or 2D, or even clusters which are in nanoscale in all 3 dimensions. All of that analysis is very easily possible using APT. It is also very useful across a large class of inorganic materials, and there is continuous research efforts to actually expand the use of APT towards organic, biological specimens, as well as solid liquid interfaces through the use of cryogenic techniques and vacuum-based transfer systems. So I'd like to acknowledge now the entire team, which has been very helpful to me and without whom all of this would not have been possible. The team Nanolab, Sihon, Jiangtao, Charlene, Xiaojie, Shangyu, Echo, the SCM dual beam teams, and the TM teams. I'd like to thank all of them for all their help and support. I'd like to take special mention to thank Jia, who was previously a scientist at Nanolab and is currently at PNNL, without whom a lot of the APT analysis would not have been possible. The Kameka service team, Fred and Kelly, for always making sure our instruments are running in the best condition. And Danny and Arun, staff scientists from PNNL, for providing some of the introductory material and helping me personally learn about APT and focused ion beam during my grad school. Lastly, let's talk a little bit about complementary techniques here, which can provide information along with atom probe in order to really strengthen analysis. And those techniques I've shown here in the color. EBST and EBIC can provide electronic information in conjunction with the chemical and spatial information that atom probe tomography provides, as well as STEM yields can provide chemical bonding and valence information in order to understand material systems better. Now, before we end for today, I would like to take a few minutes to talk about why you should choose Eurofins. The first and foremost is we take client confidentiality very seriously and ensure that our client data is protected at all times. As a company, we are a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Finally, in light of the pandemic that is affecting all of us right now, I want to stress that EAG Laboratories is committed to the safety of all our staff and our clients. Worldwide, we have complied and continue to comply with the latest COVID-19 regulations from state and local agencies, as well as the Center for Disease Control here in US. Currently, all of our locations throughout the world remain open, but we have severe limitations on customer visits. And this is a fluid situation, so we are operating our labs at reduced capacity. Based on all our discussions today for the webinar, I would highly encourage all of you to discuss your options with our sales representatives.